I want you to just take a second and imagine pulling up to a fuel station in India today.
Right.
You roll down the window, the heat of the day rushes in, and you hear that really familiar mechanical ding of the meter resetting. And, the heavy smell of hydrocarbons just completely fills the air.
Yeah, that classic petrol station smell.
Exactly. And the pump, it looks exactly the same as it did a decade ago. The nozzle feels the same in the attendant's hand. But the liquid actually flowing through that heavy black rubber hose into your car's fuel tank, it represents one of the most staggering, coordinated transformations in the history of the country's transportation infrastructure.
It really is. It's a quiet revolution happening right under our noses.
I mean, you're paying for petrol, but what you are actually pumping is this massive geopolitical and biochemical pivot disguised as just, a routine errand.
Yeah, because that liquid rushing into your tank is no longer just the refined remains of ancient compressed zooplankton dredged up from the ocean floor halfway across the world.
Right. The chemical makeup of what you are buying has fundamentally changed. And so for this deep dive, we are jumping straight into the deep end to unpack India's E20 Fuel Programme.
We really need to, because we're talking about a fuel blend that is permanently altering the entire economic and environmental trajectory of a nation of over 1 billion people.
Yes, exactly. We are going to explore exactly what E20 is, decode the actual science happening inside the engine, untangle the massive government coordination required to make this happen, and weigh the profound economic and environmental impacts based on the sources we've been analyzing.
It's a massive topic.
It is. And whether you are driving a brand new car, holding on to an older model, or just fascinated by how a country shifts its entire energy infrastructure, this deep dive is going to connect the dots between global oil markets, the chemistry of combustion, and quite literally the local sugarcane farmer.
Yeah, and the numbers driving this change are just staggering. Before we even touch the chemistry of what E20 does to an engine, we have to look at the massive, glaring vulnerability that forced India's hand in the first place.
Right, the 85% problem.
Exactly. India currently imports roughly 85% of its crude oil. Think about the scale of that vulnerability for a second.
I mean, I like to think of it like renting a house on a month-to-month lease where the landlord can just spike the rent at any moment based on things completely out of your control.
That is a perfect analogy. You're running a massive, energy-hungry industrial complex, but you have zero control over the cost of the raw energy powering it.
Right. You are entirely at the mercy of global supply chains.
And geopolitical conflicts that you have absolutely no say in. For a rapidly developing nation, relying on foreign imports for that much of your crude oil is an economic tightrope.
It really is.
When global crude prices fluctuate, whether that's due to production cuts by OPEC Plus, or conflicts in oil-producing regions, or just sudden shifts in maritime shipping lanes, India absorbs that shock instantly.
Because it's all traded in U.S. dollars, right?
Yeah. Yes, exactly. So a spike in oil prices doesn't just mean fuel costs more at the pump. It means a massive hemorrhaging drain on India's foreign exchange reserves. It physically weakens the local currency.
But hold on, let me stop you there for a second. When we talk about energy security, why the pivot specifically to ethanol? I mean, why not just drastically ramp up domestic oil exploration or, push entirely into synthetic fuels?
Well, domestic crude reserves simply cannot meet the scaling demand of India's population and industrial growth. It's just not there in the ground.
Okay, fair enough.
And synthetic fuels are still incredibly cost prohibitive at a billion-person scale. But ethanol, on the other hand, is an immediately viable, domestically producible alternative.
Right, because at its core, ethanol is just ethyl alcohol. It's a renewable, biodegradable fuel produced primarily from agricultural crops and biomass.
Exactly. So by mandating a 20% blend of ethanol with 80% traditional petrol, you are essentially replacing 1/5 of your imported crude requirement with a fuel source grown in local soil.
Which is just a massive macroeconomic hedge. You're suddenly controlling 20% of your own destiny.
Precisely.
But wait, why exactly 20%? If the goal is to cut imports and save all this foreign exchange, why not mandate E50? What is the magic about the number 20?
That comes down to the physical properties of the fuel and the limitations of legacy engineering. In the industry, it's often referred to as the blend wall.
The blend wall. Okay, explain that.
So up to about 10% ethanol, most modern internal combustion engines really don't notice a significant difference. You can pour it in and the engine just figures it out.
Right.
But once you push past that into 15% or 20%, the chemical differences between ethanol and petrol become impossible to ignore. For one, Ethanol has a higher latent heat of vaporization.
Okay.
It is also highly hydrophilic, which means it loves water, and it has a completely different stoichiometric air-fuel ratio. If you jump straight to E50, you would categorically destroy millions of existing fuel systems currently on the road.
Oh, wow. Destroy them.
Oh, absolutely. 20% is basically the absolute bleeding edge of what you can safely push through modified existing infrastructure without requiring a ground-up redesign of every single vehicle in the country.
Okay, I want to really dig into that chemistry because taking an agricultural product, something fermented from sugarcane or damaged rice, and pouring it into a highly complex, precision-engineered metal machine designed for fossil fuels, it sounds like a recipe for disaster.
It does sound crazy when you put it like that.
Right. So let's trace a drop of this E20 from the fuel tank into the combustion chamber. What is actually happening differently now?
To understand the difference, we have to look at how modern engines manage fuel delivery. When that E20 hits your tank, it is pulled by the fuel pump and pushed under high pressure toward the fuel injectors. Now, petrol is a complex mixture of hundreds of different hydrocarbons.
Right, it's a messy cocktail.
Exactly. But ethanol is a single specific molecule. It's C2H5OH.
Okay, C2H5OH, that O at the end of the formula, that's the wild card, right? Ethanol carries its own oxygen atom.
Precisely. And that single oxygen atom fundamentally alters the combustion dynamics.
How so?
Well, a standard internal combustion engine uses an oxygen sensor, or a lambda sensor, which is situated in the exhaust manifold. This sensor is constantly sniffing the exhaust gases to measure how much oxygen is left over after the explosion inside the cylinder.
Like a little scout reporting back.
Yes. It sends that data back to the engine control unit, the ECU, which dynamically adjusts the pulse width of the fuel injectors.
The pulse width meaning literally how many milliseconds the injectors stay open.
Exactly. The ECU adjusts that time to maintain the perfect ratio of air to fuel.
Okay, let me jump in there and see if I have this right. If ethanol brings its own oxygen to the party, doesn't that mean the lambda sensor is going to detect an artificially lean mixture? Like it's going to read all this extra oxygen in the exhaust and think the engine is starving for fuel?
That is exactly what happens.
Yeah.
Pure petrol requires a stoichiometric air-to-fuel ratio of about 14.7 to 1. That means 14.7 parts air to 1 part fuel for perfect combustion. But pure ethanol requires a ratio of about 9 to 1. It needs much less external air because, as you said, it already contains oxygen. So when you pump E20 into the system, the ECU sees the extra oxygen and has to immediately adapt by widening the injector pulse.
So it's dumping slightly more fuel into the cylinder to balance the ratio?
Yes, exactly.
It means the fuel injectors are working harder and you are inherently burning a larger physical volume of liquid to achieve the exact same result.
Yes, but, and this is the crucial part, the trade-off is the quality of the combustion. Because ethanol introduces oxygen evenly throughout the fuel mixture at a molecular level, you achieve a much more complete, uniform burn.
Okay, let's unpack this with an analogy. It's kind of like ethanol as a fitness coach for your engine.
A fitness coach. I like that.
Yeah, because standard petrol combustion often leaves unburned hydrocarbons behind, right? Because the air doesn't mix perfectly with the fuel mist in that tiny microsecond before ignition. It's a bit lazy. But ethanol steps in, gets everything into shape, and acts like a chemical catalyst for complete combustion.
That's a great way to put it. It aggressively reduces the presence of carbon monoxide and unburned hydrocarbons in the exhaust tailpipe. You get a much cleaner exhaust profile.
But there is another factor here too, right? The octane rating. Because drivers constantly see premium fuels marketed with higher octane numbers, and they pay extra for it. How does dumping 20% alcohol into the mix affect that?
Oh, it drastically improves it. Ethanol has a massive naturally occurring research octane number, or RON, of about 109.
Wow, 109.
Yeah. So when you blend it into standard 91 RN petrol, it significantly elevates the overall knock resistance of the mixture.
And for anyone who doesn't know, engine knock happens when the air-fuel mixture detonates prematurely, right? Under the intense heat and pressure of the compression stroke before the spark plug even fires.
Exactly. It creates a violent shock wave that can literally shatter pistons. It sounds like marbles rattling around inside the engine. But ethanol's high octane rating stabilizes the mixture, allowing the engine to run more advanced ignition timing without detonating.
And it cools the engine down internally, too. You mentioned the latent heat of vaporization earlier. Let's get into that.
Yes, this is fascinating chemistry. When liquid fuel turns into a vapor inside the intake manifold or the cylinder, it naturally absorbs heat from its surroundings.
Like sweat evaporating off your skin.
Precisely. And ethanol requires significantly more energy to vaporize than petrol does. So as the injector sprays the E20 mist, the ethanol violently absorbs heat from the incoming air charge, cooling it down.
And cooler air is denser air.
Right. And denser air packs more oxygen molecules into the cylinder, which allows the engine to produce a more powerful, controlled downward stroke. It is this amazing chemical synergy.
Okay, so the chemistry is brilliant. We have cooler intake charges, higher knock resistance, and way fewer unburned hydrocarbons escaping the tailpipe. But managing a chemical reaction in a controls laboratory is one thing. Rolling out a massive infrastructural change to over 1 billion people is entirely different.
Oh, it's night and day.
I mean, you cannot just issue a government decree and expect massive state-owned oil companies, fiercely competitive global auto manufacturers, and millions of local farmers to just instantly sync up. How do you force a whole industry into this alignment?
Well, you don't force them overnight. You basically orchestrate a bureaucratic tug-of-war spanning over 2 decades.
2 decades?
Yeah, E20 wasn't some sudden brainwave. The foundational testing for ethanol blending in India actually started with isolated pilot projects way back in 2001 and 2002.
I had no idea it went back that far.
They slowly introduced a 5% blend, E5, around 2003, but it really languished for years. There were constant supply chain inconsistencies. The real turning point, the aggressive push we're seeing now, was formulated by NTIOG.
The government's premier policy think tank.
Exactly. They drafted the 2020 to 2025 roadmap, which completely changed the pace of the rollout. We achieved E10 in 2022, and then in February 2023, PM Narendra Modi officially launched E20 at India Energy Week, targeting a full nationwide rollout by 2025.
But let me play devil's advocate here. It's one thing for ministries and think tanks to write roadmaps and give speeches. NETI-IOG doesn't own refineries or gas stations. Getting massive oil companies and the auto industry to play along sounds like a logistical nightmare. Who actually enforces this?
This is where the massive structural leverage of the Ministry of Petroleum and Natural Gas comes in, the MoPNG. They are the commanders in this scenario.
Okay.
They dictate terms to the public sector oil marketing companies. We're talking about massive entities like Indian Oil Corporation, Farad Petroleum, and Hindustan Petroleum. And the logistical nightmare those companies face to adapt to E20 is hard to overstate.
But why? It isn't just about dumping ethanol into a massive storage tank and stirring it. They blend additives into fuel all the time.
No, because of ethanol's affinity for water, which we touched on a minute ago. Legacy underground storage tanks at retail petrol stations inevitably contain trace amounts of moisture from condensation. It's just a fact of life. If you put standard pure petrol in that tank, the water just sits at the bottom, completely harmlessly separated because oil and water don't mix.
But ethanol loves water.
Ethanol loves water. If you introduce E20 into an old, unclean tank, the ethanol strips the water right off the bottom, binds with it, and suspends it in the fuel.
And if that water-ethanol emulsion gets sucked into a car's fuel pump?
It causes engine misfires, rough idling, and potentially catastrophic internal corrosion. And it gets worse. If the mixture absorbs too much water, it hits a saturation point and triggers something called phase separation.
Phase separation. What does that mean for the fuel?
It means the ethanol water compound completely drops out of the petrol. It sinks to the bottom of the tank as this highly corrosive sludge, leaving incredibly low-octane, damaged petrol floating on top.
That sounds like a mechanical nightmare. So the oil marketing companies couldn't just use their old equipment. They had to overhaul their entire storage infrastructure just to handle the new liquids safely.
Exactly. They had to transition from top loading to bottom loading at terminal depots to reduce vapor emissions. They had to utilize specific internal floating roof tanks. They even had to recalibrate their massive mass flow meters because the specific gravity of E20 is different from pure petrol.
So the oil companies are spending billions upgrading their end. But what about the cars themselves?
That fell to the Ministry of Road Transport and Highways, MORTH. They were the regulators here. They laid down the gauntlet, mandating that auto manufacturers adapt their vehicles to handle the corrosive properties of this new fuel by 2023.
Okay, so we've got the think tank, the petroleum ministry, the transport ministry, and the oil companies all coordinating. But I want to look closely at where this fuel is actually coming from, because this is where the policy stops being just an energy initiative and becomes a massive lever for the rural economy.
It completely reshapes the agricultural sector.
Right, because we are essentially replacing oil fields with agricultural fields. But my immediate thought is, aren't we just robbing Peter to pay Paul? I mean, if you divert massive amounts of sugarcane and maize to feed internal combustion engines, aren't you inevitably causing a food shortage?
That is the crux of the global food versus fuel debate. And you're absolutely right, it is a highly volatile issue. If a policy blindly incentivizes ethanol production from staple food crops, it absolutely drives up food prices and threatens food security.
Especially in years with weak monsoons or poor harvests.
Exactly. But India's strategy to mitigate this risk is really clever. It's heavily focused on utilizing specific byproducts and damaged crops rather than premium food-grade harvests.
Okay, let's define that for the listener. When we say byproducts, what exactly are the distilleries using?
So the backbone of the industry has historically been molasses, specifically what is known in the sugar industry as C-heavy molasses.
Molasses.
Yeah, when sugar cane is crushed and the juice is boiled to extract crystallized sugar, you are left with a dark, viscous syrup. After multiple rounds of boiling, the remaining syrup, which is the C-heavy molasses, has very little recoverable sugar left.
So it's basically the dregs.
Basically. For decades, it was a low-value industrial byproduct. But the ethanol program suddenly turned that waste into high-value energy feedstock.
But wait, C-heavy molasses alone couldn't possibly meet the demand for a nationwide 20% blend. There's just not enough of it.
You are absolutely right. To meet the E20 targets, the government had to widen the net. They permitted the use of B-heavy molasses, which still contains a significant amount of recoverable sugar, and even direct sugarcane juice in years of massive surplus.
But even then, tying your national fuel supply entirely to the sugarcane crop seems risky.
It is, which is why the real game changer and the release valve for that food versus fuel tension has been the pivot toward grain-based ethanol, specifically utilizing damaged food grains and broken rice.
Damaged food grains. Are we talking about grain that has literally rotted in storage?
Yes, unfortunately. In any agricultural system operating at the scale of India's, millions of tons of grain are lost to poor weather during harvest, pest infestations, or inadequate warehousing. This grain is totally unfit for human consumption.
Right.
Previously, it represented a catastrophic financial loss for the farmer and the state procurement agencies. It was just garbage. Now, through enzymatic hydrolysis and fermentation, the starches in those rotting grains are converted into fermentable sugars and then into ethanol.
That is brilliant. It fundamentally changes the economic floor for the agricultural sector. Waste is instantly monetized.
Exactly. Instead of rotting, it's liquid energy.
Yeah.
It leads to new distilleries, rural employment, and much better crop prices for farmers.
So the farmer gets a guaranteed safety net for damaged crops, which is fantastic. But what about the environmental cost of this massive agricultural industrialization? We talk about tailpipe emissions going down, but aren't distilleries massive industrial polluters themselves?
They certainly can be.
Right, because if you factor in the diesel burned by the tractors harvesting the sugarcane, the massive amounts of water used in irrigation, and the energy required to boil and distill the ethanol, does the net carbon calculation actually hold up?
That is what scientists call the life cycle analysis, or LCA, and it is fiercely debated in the academic community. You are completely correct to point out that ethanol production is highly energy and water intensive.
Sugarcane especially, right?
Sugarcane has an immense water footprint. In states like Maharashtra and Uttar Pradesh, sugarcane cultivation puts severe stress on already depleted groundwater tables. And if the electricity powering the distillery comes from a coal-fired power plant, well, the net greenhouse gas reduction of the ethanol drops significantly.
So we are essentially just moving the carbon emissions from the city traffic jam to the rural power plant.
It is not a perfect one-to-one transfer, but you're right. The offset is not as clean as purely looking at the tailpipe suggests. However, advanced distilleries are mitigating this by operating as closed-loop systems.
Closed-loop systems, how does that work?
They take the bagasse, which is the fibrous, woody residue left over after crushing the sugarcane, and they burn it in high-efficiency cogeneration boilers to power the distillery itself.
Oh, so they power themselves with their own waste.
Exactly. And any surplus electricity is actually fed back into the regional grid. Furthermore, they process the spent wash, the highly toxic liquid waste, from distillation into potash-rich fertilizers, which are then sold back to the farmers.
Wow, so they're really using every part of the buffalo, so to speak.
They have to. When optimized, the life cycle carbon intensity of ethanol is significantly lower than that of extracted, refined, and transported crude oil, but it requires relentless regulatory oversight to ensure distilleries aren't taking environmentally destructive shortcuts.
I see where you're going with that, and it makes sense on a macro scale, but let's bring this back to the immediate reality for the listener. Because I'm sitting in my car and I'm just filled up with E20. You mentioned earlier that ethanol inherently requires a richer air-to-fuel ratio because it contains oxygen, right? The fuel injectors are dumping more liquid into the cylinder. The math on that seems totally unavoidable. My fuel efficiency has to go down.
The math is indeed unavoidable. We're talking about the lower heating value, or LHV, of the fuel. The energy density of pure ethanol is roughly 30 to 35% lower than that of pure petrol by volume.
30 to 35% lower.
Yes. So when you blend 20% of this less energy-dense liquid into the petrol, the overall volumetric energy density of the blend drops. For the everyday driver, this translates to an estimated 3 to 7% decrease in fuel efficiency.
So wait, I have to fill it more often. I am paying the same price at the pump, but I am getting fewer kilometers per liter.
Yes, that is the direct trade-off of the program. Modern vehicles equipped with advanced engine management systems and direct injection can mitigate some of this loss by optimizing spark timing, and they take advantage of the higher octane rating to run higher compression ratios. But the immutable laws of thermodynamics remain. You are literally carrying less chemical energy in the same size fuel tank.
Okay, slightly worse mileage is, annoying, but it's probably not a deal breaker for most people given the broader benefits. What I am far more concerned about is compatibility. You mentioned earlier that more force auto manufacturers to adapt. If I am driving a brand new 2024 model from Maruti Suzuki or Hyundai or Hero, I assume I'm perfectly safe.
Fully safe. Vehicles manufactured from 2023 onward that carry an explicit E20 compliance certification are engineered specifically for this chemical environment.
What does that mean practically?
They possess upgraded ECU software to seamlessly handle the altered stoichiometry we discussed. But more importantly, they feature robust material upgrades. They use ethanol-resistant fuel lines, specialized injector nozzles, and highly resilient polymer seals designed to withstand the solvent properties of alcohol.
Okay, but what if I'm not driving a brand new car? What if I am driving, say, a 2015 model that was engineered before anyone was seriously thinking about a nationwide E20 mandate? Is this fuel going to eat my engine from the inside out?
It is not going to dissolve your engine overnight, no. But the risk of accelerated degradation is very real. We discussed ethanol's hydrophilic nature, its tendency to absorb water from the atmosphere.
Right.
When water enters a legacy fuel system, it introduces oxygen and moisture directly to bare metal surfaces. Furthermore, ethanol itself is electrically conductive, unlike pure petrol.
Wait, ethanol conducts electricity?
It does. So when you have different metals in a fuel system, say aluminum components touching steel components, and you immerse them in a conductive fluid like ethanol, you create a tiny battery.
A battery? Inside the fuel line?
Yes. You induce something called galvanic corrosion. The electrical potential difference between the dissimilar metals causes one of the metals to rapidly corrode. In older cars, the aluminum components inside fuel pumps or carburetors can literally pit and degrade.
That is just wild to me. It's literally eating the engine from the inside out.
Yeah, literally. And it's not just the metal. Ethanol is a potent solvent. It interacts poorly with older elastomers, materials like nitrile rubber or certain plastics used in gaskets, O-rings, and fuel hoses.
Because it's alcohol, so it's a degreaser.
Exactly. Over time, the ethanol leaches the plasticizers out of the rubber, causing the seals to become brittle, shrink, and eventually crack, which leads to dangerous fuel leaks.
That is deeply concerning for anyone holding on to an older vehicle. It essentially forces a massive hidden maintenance cost onto the public. I mean, if I have an older car, I'm suddenly risking fuel pump failure or deteriorated hoses just by using the only fuel available at the station.
It highlights the friction of any transitional period. The government advisory states that older vehicles can run on E20, but it comes with a warning of decreased fuel efficiency and potential long-term material wear. It places the onus on the consumer to meticulously maintain their vehicle and perhaps preemptively upgrade vulnerable fuel lines.
It is a calculated casualty of macro-level policy.
That's a good way to put it, yes.
Which brings up a really critical question about the future. If E20 lowers fuel economy, risks damaging legacy infrastructure, and constantly dances on the edge of the food versus fuel debate, is this actually the end goal? Are we going through this massive logistical agony just to be stuck at 20% ethanol forever?
No, definitely not. If you view E20 as the final destination, the trade-offs seem totally overwhelming. But E20 must be understood as a transitional bridge. It is a pragmatic stopgap.
A bridge to what?
The ultimate destination for global transportation is zero tailpipe emissions. We're talking battery electric vehicles, hydrogen fuel cells, and perhaps advanced synthetic e-fuels.
But you can't just flip a switch and put 1 billion people in electric cars tomorrow.
Exactly. The infrastructure required for a fully electric national fleet, the lithium supply chains, the massive grid upgrades, the deployment of millions of fast chargers in rural areas, that will take decades to fully mature.
Right.
In the meantime, you have hundreds of millions of internal combustion engines currently on the road, spewing carbon and draining foreign exchange. E20 acts as an immediate deployable mitigation strategy. It buys time, it immediately lowers the carbon intensity of the existing fleet, while the technology of tomorrow scales up.
But does the ethanol itself get any better? Because if we are stuck with internal combustion engines for the next 2 decades, are we going to be locked in a permanent battle over sugarcane and damaged grains?
That is where the science gets incredibly exciting, and it involves shifting from first-generation ethanol to second-generation, or 2G ethanol.
You've heard of G ethanol. Okay, what's the difference?
Well, first-generation ethanol relies on fermenting simple sugars and starches things humans or livestock could theoretically eat. Second-generation ethanol breaks that paradigm entirely. It utilizes lignocellulosic biomass.
Lignocellulosic biomass. You're going to have to break that down for me.
We are talking about the incredibly tough structural components of plants. Agricultural residues like wheat straw, rice husks, corn stover, and bamboo.
The stuff you can't eat.
Exactly. This is material that is completely inedible and is historically just burned in the fields by farmers, causing massive air pollution crises in northern India every winter.
But how do you get alcohol out of dry, woody stalks? There is no sweet juice or starch to ferment.
It requires an incredibly complex biochemical process. The cellulose in these agricultural residues is locked behind a tough, protective shield of lignin and hemicellulose. You cannot just add yeast to it. The yeast wouldn't know what to do. So a 2G ethanol biorefinery, first, has to subject the biomass to extreme heat and chemical pretreatment to shatter that lignin armor. Then, they introduce highly specialized, genetically engineered enzymes to perform enzymatic hydrolysis.
Enzymatic hydrolysis.
Yes, these enzymes act like molecular scissors,
Yeah.
literally snipping the complex cellulose chains into simple, fermentable sugars. Once you have those simple sugars, you can ferment them into ethanol, just like you would with molasses.
That is unbelievable. So 2G ethanol takes the most stubborn, polluting agricultural waste, subjects it to intense biochemical engineering, and produces high-grade fuel, completely bypassing the food versus fuel debate.
Precisely.
You are literally turning field trash into national energy security.
The challenge right now is simply the capital expenditure. 2G biorefineries require a massive upfront investment, and the enzymes themselves are highly proprietary and expensive. But as the technology scales and becomes cheaper, 2G ethanol will systematically replace first-generation ethanol. It will stabilize the agricultural markets and drastically improve the life cycle carbon emissions of the E20 program.
It really puts the entire scope of this policy into perspective. We started this conversation looking at a simple fuel pump, but the reality is a sprawling web of biochemistry, global macroeconomics, and agricultural engineering.
It's massive.
It is an imperfect solution, right? I mean, there are efficiency drops and mechanical risks for older cars, but it is a deeply pragmatic one.
It forces us to rethink our definition of infrastructure entirely. We are so accustomed to viewing energy as something extracted from the earth by multinational corporations. The E20 program decentralizes that. It integrates the farmer into the energy supply chain, shifting wealth from international oil markets directly into the rural economy.
As we wrap up this deep dive, I really want you, the listener, to think back to that fuel station we talked about at the beginning.
Yeah.
The next time you are driving out of the city and you look out your window and see a vast field of maize or tall stalks of sugarcane swaying in the wind, or even if you read a headline about a surplus of damaged, unusable rice, don't just look at it and see a harvest or a food supply chain or an agricultural loss. Ask yourself, are you actually looking at millions of barrels of crude oil that a nation will never have to import? Are you looking at the localized biochemical future of national energy security engineered right out of the soil? Because the answer, increasingly, is yes.
Well said.
Thanks for joining us on this deep dive. We'll see you next time.